So maybe we could do this. Those are equal, aren't they? I've added and subtracted that, added and subtracted that. Usual little tricky stuff. True? Now, let's use the generalized triangle inequality. Instead of splitting this into two pieces, I'll have three absolute values. Where shall I put them? Like this. So this is evidently less than or equal to the absolute value of the pointwise limit function evaluated at x minus one of the sequence functions evaluated there, plus the difference between the one of the functions in the sequence that's known to be continuous evaluated at the x point, and then the same thing evaluated at the target point. And then finally, that. Right? Okay, now if I can keep each one of these less than epsilon over 3, I can make the whole shebang less than epsilon. How can I do that? What would the justification be? Well, this one, and this one depend on uniform convergence. This one depends on continuity of a member of the sequence, right? You see that? See that, Sandy? This one, I'm saying, remember, it converges uniformly. That means you can go out and find an n, such that once you're past that n, for any point x, the difference between the nth term here in the sequence and the pointwise limit is less than a pre-assigned epsilon. So fine, I'll make it epsilon over 3. And I'll do the same thing here. This is just another point in the domain where it's uniformly convergent. Right? At x and x naught, I want to pull the lever on uniform convergence, which says this thing. I mean, remember how you got this? It was the limit as n went to infinity of this thing. Oops. Is it doing anything? No, don't want that. If you touch it, you get excited. Touch it. Sometimes it lights up black or something. Okay. So we got this pointwise limit by running this thing out with n. So the fact that it's uniformly convergent means that no matter what x we have in our domain where this happens, I can run out and get past one particular capital N of epsilon. And as long as I get past it, this will be true. It will be less than pre-assigned epsilon. As well as here, this is just another point in the domain. So I'm using the same argument for both of these. Uniform convergence puts this guy close to him and this guy close to him. Oh, this guy close to him. Right? This is the pointwise limit, and I'm sneaking up on it with the FNs. So I can go find that big N of epsilon over 3. So this is less than epsilon over 3. This is less than epsilon over 3. How about this one? That's one of the continuous functions out there. It has nothing to do with the pointwise limit. But he's continuous. Where is he continuous? Well, he's continuous at x0, right? X naught. So I can go find a delta, right? To keep that less than epsilon over 3. And then they're all less than epsilon over 3. There's 3 of them, so the whole shebang is less than epsilon, but that majorizes this expression up here, so it's true. So the other guy, the pointwise limit, is continuous as well as the sequential functions. That's Weierstrass's theorem. It's very useful. Very useful. The converse is not true. But there is a weak converse. It goes like this. If you have a closed interval and a sequence of functions that are continuous, and they converge pointwise to a known continuous function, then the convergence is uniform. Right? Weierstrass's theorem says if you have continuous functions and they converge uniformly, the limit function is continuous. The weak converse is not that if you have a uniformly convergent sequence of functions to a continuous function, what is the converse of that anyway? You want to conclude uniform convergence. So if you have a continuous limit function and continuous sequence functions, the converse would be if the pointwise limit of the sequence is the continuous limit, then the convergence is uniform. You can't quite make that statement. You have to have the functions defined on a compact set, and they have to monotonically approach the limit function. They can't be every which way. They have to move up. I mean, they can move up this way, but every one has to either go up or down to the limit function. That's called Dini's theorem. Dini's criterion for uniform convergence. Ulisse Dini was an Italian mathematician. Sure wasn't Irish. And he invented some neat stuff like the derivatives of Dini. The derivatives of Dini. Doesn't that sound great? That almost ranks up there with the zonules of Zinn. Sounds like some kind of science fiction. The zonules of Zinn are those little funny things in your iris, aren't they? Little flecks. No, not the floaters in there. Ventris humor, but the iris itself. The zonules of Zinn. Well, math has got some of those. The derivatives of, not derivatives, the derivatives of Dini. And what you do is, even if a function isn't differentiable at a point, you form the difference quotient, and you take the supremum of the difference quotients as you approach from the left, the infimum as you approach from the left, the supremum as you approach from the right, and the infimum as you approach from the right. If all four of these things are of the same thing, that is differentiable. If two on one side are the same, then it's laterally differentiable from that side. If all four are different, well, you're just out of luck. But you have the four things. You have the derivatives of Dini. Anyway, that's not important. I did.
Yeah, there was a theorem.
Dini's theorem. Who would like to explain Dini's theorem to us on Tuesday? You don't want me to just talk for 2 hours, do you? You're gonna do what? Yeah. I forgot what it is.
Tomei function.
The Tomei function.
Proving that it's
Tomei's function.
continuous on the rational.
Right. Matt, Tomei. Who wants to do? I actually think Tomei was a Dane, so his name would be written like this, with one of those Danes. Yeah. Who wants to do Dini's theorem? It's a beautiful little theorem, and it's probably more your analysis. I'm sure it's Wade. You got Wade.
Yeah, we know.
Who wants to do that? It's already there? Oh, okay. There you go. Okay. Who wants to do Dini's theorem? It hasn't done anything yet. You want to do it? Okay. He's gonna present. Go find Wade. grade it's in there and present Diddy's theorem. It depends on the compactness. Well, you do it your way, and I might have a niftier proof based on